Hello learners, once again I welcome on the class of fluid mechanics. So I hope you all are safe and doing well. So today I am going to discuss another new topic, that is laminar flow through pipe. So in laminar flow through pipe, firstly I will discuss what is Reynolds number, and with the help of this Reynolds number I will discuss whether our flow is laminar or turbulent, and after that I will discuss the two fixed parallel plates at a distance of h, and in the parallel plate I will discuss the velocity distribution, and after that condition for the maximum velocity, expression of maximum velocity, and the expression of shear stress and expression of maximum shear stress, and after that with the help of that we can compute the head loss and power in the pipe. After that I will discuss the circular pipe. In circular pipe same thing I will discuss, like velocity distribution, shear stress distribution, maximum velocity condition, and after that I will discuss the what is the head loss in the circular pipe, and after that I will take some problems based on the parallel plates and circular pipes. So today I am going to discuss about the laminar flow through pipes. So in the pipe flow, the characteristics dimension is diameter of the pipe. Diameter of pipe. And Reynolds number can be computed as rho Vd by mu, or in terms of kinematic viscosity Vd by nu. With the help of this Reynolds number we can classify either our flow is laminar or turbulent. Once the Reynolds number is less than 2000, then our flow is laminar in pipes, or if the Reynolds number is greater than 4000, it means the flow is turbulent in the pipe, and if the Reynolds number lies between 2000 to 4000, then there is a transition flow. So if Reynolds number can be, rho is the density, v is the velocity, d is the diameter of pipe, and mu is the dynamic viscosity of the fluid. V is the velocity, d is the diameter, and nu is the kinematic viscosity of the fluid. The unit of the dynamic viscosity we have already discussed, that is Newton second per meter square or poise, and the unit of the kinematic viscosity can be written as centimeter square per second or in Stokes. So if Reynolds number less than 2000, our flow is laminar, and if the Reynolds number greater than 4000, flow is turbulent. And if the Reynolds number lies between 2000 to 4000, then there will be transition flow. So remember in mind that this value is valid for the pipe flow only. For different mediums the Reynolds number will be different for the condition of laminar and turbulent. Like if I will discuss about the boundary layer, so if the Reynolds number is less than 5 into 10 to the power 5, then our flow is laminar. If I will discuss in the soil, then when our Reynolds number is less than unity, then our flow is laminar. So it will be vary. So I have written this value for the pipe flow. Laminar flow between two parallel fixed plates. So next studying is laminar flow between two parallel fixed flow. Once we have decided the flow is laminar, then I am interested to know the velocity, shear stress each and everything in the plate laminar flow between two parallel fixed plate. So let us assume this is our parallel fixed plate. This is fixed and this is also fixed. This is the center of the plate, x direction, and this is the y direction. Velocity is flowing and the distance between these two parallel plates is h. So I am interested to compute the velocity profile or distribution. So let us assume this is dx and this is dy, and this is at a distance of y from the bottom fixed plate. So I have taken the fluid element. This is our fluid element system. So if I draw the free body diagram of this fluid element, so this is our fluid element. So the force in this direction is P into dy, and in this direction is P plus del P by del x into dx into dy. And this is, of course, this is for the unit length, and this is for the unit length. And once the flow is in direction, the shear stress will act in this direction, and the magnitude will be tau into dx into 1. And similarly in this direction, shear stress will be tau plus del tau by del y into dy into dx into 1. So this is the free body diagram. So if I equate the force in the direction of flow, so in the direction of flow, as the flow is uniform, so V is constant because of uniform flow. So once the V is constant, so the acceleration is 0. Once the acceleration is 0, so force is equal to 0 in that direction. So we can write force in that direction is P into dy minus P plus del P by del x into dx into dy minus tau into dx plus tau plus del tau by del y into dy into dx is equal to 0. So P dy and P dy is cancel. So minus del P by del x plus del tau by del y is equal to 0. Del tau by del y is equal to del P by del x. And if I put the value of shear stress, we know that shear stress is equal to mu du by dy. So if I put the value of shear stress in the equation, so the equation will look like del by del y into mu du by dy is equal to del P by del x, or we can write del 2u by del y square is equal to 1 by mu into del P by del x. Integrating the equation, integrating both sides, so it will look like del u by del y is equal to, here x is constant, so y by mu into del p by del x plus c1. Once again integrating on both side. So it is u is equal to y square by 2 mu del p by del x plus c1x plus c2. So once we compute this constant c1 and c2, then we will get the expression of velocity when our flow is between two parallel fixed plate. So boundary condition we have to apply for the boundary condition. So what is the boundary condition? At y is equal to 0, our velocity will be 0. So, and the second boundary condition, at y is equal to h, our velocity is once again 0. So first boundary condition if I apply, so C2 will be 0. C2 is equal to 0 and C1 is equal to minus h by 2 mu del p by del x. With the help of these two boundary condition, we have computed the two constants. So the expression of velocity by equation first. So expression of velocity is equal to y square by 2 mu del p by del x minus h into y divided by 2 mu del p by del x. So take it out common, del p by del x. So 1 by 2 mu minus 1 by 2 mu del p by del x. So it is coming hy minus y square. So the velocity, general form of velocity between two fixed parallel plate is 1 by 2 mu minus del p by del x into hy minus y square. So this is the equation of velocity, where mu is the dynamic viscosity, h is the distance between parallel plate, So if I draw the distribution of velocity in parallel plates, so let us assume this is our fixed parallel plates. This is the center line, distance is h, and this is y. So if I draw the distribution, so when y is equal to 0, our velocity is 0, and when y is equal to h, our velocity is 0, and the maximum velocity will occur at the center. So this is our velocity distribution. This is maximum velocity, u profile, so we can write when y is equal to 0, u is equal to 0, when y is equal to h, u is equal to 0. We have already discussed the boundary condition we have taken. For maximum velocity, y is equal to h by 2, u is equal to u max, and u max is equal to 1 by 8 mu minus del p by del x into h square. Put the value of y is equal to h by 2 in the general equation of the velocity, that is 1 by 2 mu minus del p by del x into hy minus y square. So this is the maximum velocity in the parallel plates. Now I am interested to derive the expression of shear stress. So shear stress distribution. Shear stress distribution. So according to the Newton's law of viscosity, we know shear stress is equal to mu into du by dy, or we can write tau is equal to mu du by dy. We can write it is minus 1 by 2 mu del p by del x into h minus 2y, because velocity distribution is 1 by 2 mu minus del p by del x into hy minus y square. So once we derive, so shear stress is equal to minus del p by del x into h by 2 minus y. So this is the general equation of shear stress. So the nature of the shear stress is linear, but the nature of velocity is parabolic. So when it will be maximum and when it will be 0. So when y is equal to h by 2, the shear stress will be 0. When y is equal to h by 2, shear stress is 0. When y is equal to 0, tau is equal to tau max, maximum shear stress. So if I draw the shear stress distribution, so this is our parallel plates. This is our center line. So the distribution of shear stress, as I told you, it is linear, maximum, and it is 0. So this is our shear stress distribution. Shear stress profile. After that, I am interested to compute the mean velocity or average velocity, mean velocity or average velocity. So what is mean velocity? The mean velocity, that constant velocity at the section which is crossing same mass flow rate as it is crossed by actual velocity, is known as mean velocity. So in parallel plates, average velocity is 2/3 of maximum velocity. If I integrate or if I compute the mass flow rate, so you will get the expression of average velocity. So average velocity is equal to 2/3 of maximum velocity, and maximum velocity is 1 by 8 mu minus del p by del x into h square. So average velocity is equal to 1 by 12 mu minus del p by del x into h square. So this is our expression of average velocity in the fixed parallel plates. Similarly, we can compute the head loss between two sections in the direction of flow. So if I compute the head loss between two section in the direction of flow. So this is our parallel plates. This is our section first, and this is second section, and this is our flow. So we know that average velocity is equal to 1 by 12 mu minus del p by del x into h square, or we can write minus del p integral of p1 to p2 is equal to 12 mu into u average divided by h square del x, running from 0 to L if this distance is L. So we can write P1 minus P2 is equal to 12 mu into u average into L divided by h square, P1 minus P2, or we can write P1 minus P2 divided by gamma is equal to 12 mu into u average into L divided by gamma into h square, and P1 minus P2 by gamma is the total head loss. So this is our head loss HL. So HL is equal to 12 mu into u average into L divided by gamma into h square. This is our expression of head loss of head between the parallel plates. So briefly, if I will write for parallel plates, if write the expression of generalized velocity expression, so 1 by 2 mu minus del p by del x into hy minus y square. Similarly, expression of shear stress is minus del p by del x into h by 2 minus y. Similarly, average velocity is equal to 2/3 of maximum velocity, and the maximum velocity is 1 by 8 mu minus del p by del x into h square, and the expression of average velocity is equal to 1 by 12 mu minus del p by del x into h square. And similarly, if I write the head loss, so head loss is equal to 12 mu into u average into L divided by gamma into h square. So this expression we have to remember for the parallel plates, and we have also seen the velocity profile and shear stress profile in this context. So dear student, today I have discussed what is the Reynolds number. So Reynolds number is the ratio of inertia force by viscous force, and in pipe flow, so I have derived the Reynolds number, that is rho Vd by mu, where rho is the density, v is the velocity, d is the diameter of pipe, and mu is the dynamic viscosity. So once our Reynolds number value is less than 2000, then our flow is laminar, otherwise it is turbulent. So in this chapter I will discuss the laminar flow through pipe. After that I have derived the velocity distribution, shear stress distribution, what is the condition for maximum velocity, what is the average velocity, and what is the head loss between parallel plates. So in parallel plates we have seen the expression of velocity, that is 1 by 2 mu minus del p by del x into hy minus y square, and with the help of this expression we have seen our distribution is parabolic, where our velocity is maximum at the center line. And similarly I have derived the maximum velocity And after that I have derived the expression of shear stress, that is minus del p by del x into h by 2 minus y. With the help of this we have show you that the distribution of the shear stress is linear and the maximum shear stress condition. And after that I have derived the max head loss between the two parallel plates, that is the expression of head loss is 12 mu dual by gamma h square. So in the next class I will discuss the same velocity distribution profile, shear stress distribution condition for maximum velocity, what is the expression of average velocity, and what is the head loss in circular pipe. So take care of your health and happy learning.